For this next problem, I'm just going to set it up. You see the little star next to the thing up there? That means it should be a computer-based problem. And so they got up to a certain point and they said, forget about it. I'm just going to go ahead and plug this into a computer. But we do want to use this as sort of a jumping off point, or as a review of using the rigid body, free body diagram aspect of the thing. So let's try or do our best. We'll set it up and then get to a point where we don't want to bother and be done with it. I actually wrote the word punt on my piece of paper, so you don't believe me, I can show that to you. So anyway, read this problem where we have this base motion here of YB right there. It's going to be moving the thing up and down, and our meter is connected at O as like a cantilever, not quite cantilever, we have a little beam operating on here, and it's supported by a spring and by a damper, and it's got this weight over here, and then it's got this little extension, little rubber thing onto there. So the dimensions are, this is 1.2 feet, this is 1.6 feet, and this is 2 feet right there. The weight is 2 pounds, the damper is 0.1 pound second per foot, and this thing is moving, this omega, which is the omega F. Omega F is going to be equal to 10 radians per second. Right. Determine the range of spring constant K over which the magnitude of the recorded relative displacement is less than 1.5. It is assumed that the ratio omega n must be greater than unity. All right, so we're not going to be able to solve and get this value right here. We're going to get kind of a little bit stuck. They said to use a computer to try to solve it, and I guess I can. I could probably have made an Excel thing and then just did a goal seek and then found out what kind of K I needed. But here's the beginning of the thing: is an FBD and an IBD, and I'm going to pick a location right here, an angle of going upwards, and it's in the act of moving upwards. So we're going to go like that right there, and I will have, let's see, supports right there of a Roy and rocks. Going to have a weight of the rod and a weight of this, but I don't think they told us the weight of the rod, so we're going to assume that it doesn't matter. And so this is going to be the weight of the thing coming down. I already used a W. We will say the spring is coming this way. Let me change colors. I like to change some colors in these things. The spring is pushing down on this with a K times L1 theta, whereas the damper is pulling down. That's a CL1 theta right in there. And anything else? Just a quick note right over here, right in green, that we're going to go, we neglect this. Remember that. We neglect due to static deflection, right? So when it was in its equilibrium position, it was horizontal, and therefore there was already a certain amount of static deflection of the spring. And when we go through, and we could have kept it in there, but it just makes our process longer. So we're not going to do it because we don't want to. All right. Now, we have a little bit of a, trying to see if I'm going to say this the right way. We have two things going on. All right, so this makes it a different problem from some other problems because this whole housing is accelerating, right? and we could call this a y double dot right there. So not only do so I'll put it right here, although it should be at the center of mass of the whole thing, truth be told. It is, and where did I put it? That's an interesting thing. Well, I guess if you're going to assume that the rod is massless, we're going to have right here, we're going to have the mass of it times that double dot, but we're also going to have the mass of the thing times L2 theta double dot. Right, sort of an interesting type of twist that we have to deal with. Anything else? I don't think so. Okay, so right, so now hopefully I gave you sort of a hint of why we had to do those both things, because this thing is accelerating right here, but then also the whole thing is accelerating. So in terms of the motion that's happening onto the piece, it's because of that baseline motion. So the sum of the moments about O is equal to the sum of the effective moments about O. And looking at this right here, it appears to me on the left-hand side, those are going to be clockwise. So we got K, well, actually, we should probably do the C first. Let's do the C, L1 theta, but those are forces, so we need moments. So there's another L put onto there. And the same thing for this K, L1 theta. Oh, but that should be theta dot. I forgot to make it. I forgot the dot. Sorry, because it's based on velocity, right? And then there, I almost forgot the square here. It's going to be equal to this mass times length 2 theta double dot. But once again, that this is an inertial force, so it needs to be turned into a moment. So we multiply by that. We also have a mass of that thing, right? Or it's the weight divided by 2. Divided by 32.2 for us, right? And it's going to be, how did I write it first? I wrote it as L times Y double dot, right? So this is L2. Not squared because it's already my double dot, right? So we could set this up for the equation of motion. I'll just move it around. Then you got plus C L1 squared theta dot plus K L1 squared theta is equal to a negative M L2 Y double dot, right? So that's kind of a standard thing. Now I had to play around with a little bit of monkey business. We will take the fact that if we analyzed this piece right here, we would say, okay, well then y is equal to, well, let's call it a big Y instead of that B that they have, sine of omega ft. We get y dot is equal to y, negative y, no, not negative y yet. Okay, so actually the book uses cosine. I guess I could just go ahead and use the cosine, doesn't really matter, onto the thing. One of the nice things is we get rid of the negative sign if we decide that we're going to make it a cosine, is how we're going to make the fit. So we got a negative there with an omega f sine omega ft, and then we get a y double dot is equal to negative y times omega f squared cosine. And then we just use a cosine throughout the whole thing right there and replace this with the piece, with it. We can also divide through if we want to make one additional step. So we say a theta double dot plus C, this can be L1 squared over M L2 squared, they don't cancel out, theta dot, plus K L1 squared over M L2 squared, theta, and then this one over here, we replaced this y with the function right in there. So we get, so the m's actually cancel out. And we're going to have a y. So we're going to have a y, and one of the l's cancels out. So there's L2 right in there because there was an L2 squared, but we've divided out here as an L1, right? L2 right there. So only one of them cancels out. And then we're also going to replace the omega f squared, and then it's a cosine of omega ft. And I think that's about as far as I would want to see that you're capable of doing in setting the thing up. Really, the complication becomes that we can't find the natural frequency just yet because we don't know the K. And we have this term right here. This is difficult to break down and get into the exact form. I think you could probably stare it down and get it placed into the thing. But I didn't. I decided to go just this far and say this is enough. And this is my intention of a problem like this. Although this did have the little wrinkle. Something that you would note that we didn't use, that you used towards the end of the thing, is that the actual displacement, when we got to a solution that gave us the form of the thetas as a function of time, or as a solution for theta, the magnitude of theta, I should say, we want to make sure we multiplied that by L3 for the distance that the thing would move, because it's a little longer, right? So we pretty much put up the same form that we had for all those others, and then come up with K. If they had given us K, this problem would have been doable, but because we don't know it yet, there's several other things that we would have to go through algebraically, and it's better to just use a computer on it. But the reason why I included it, or I decided to go ahead and do it as an example, was because it was necessary. It was worthwhile as an example on how to do one of the rigid body problems. And I'll do another rigid body problem, I think, is the next one. It, too, was a little bit on the complicated side. Not impossible to do, just it's actually pretty easy right up to the point where they asked the little add-on. So we'll see in the next problem. And this guy right here, he looks like a little bit of a smiley face right there. He's kind of like sticking out his tongue or something.